do complete today. Along the way, I have to make a lot of assumptions, wave my hands a little bit, go over proofs, and that's the way it would work. Okay, so last time we saw something about the structure of subsequent algebra, how root spaces are necessarily one-dimensional, and if alpha is root, no multiple of alpha can be root, other plus and minus alpha. That's what I think we did. And we also, in proving that, we needed the classification of irreducible representations of set to C. The 1D subscript group. Okay, today I want to talk about the representations of an arbitrary simple group or compact group or equivalently that of a complex simple algebra. We saw that complex representations of complex simple algebras are the same as representations of compact simply connected simple groups. So let me now fix G C to be complex very simple. But other notation we have this maximal the ability algebra, maximal ability algebra. So these algebra you see coming from a compact course. G compact group and simplicity group and T is a torus. We'll also assume that G is simply connected. TC is same as T tends to C over R. And T is the real algebra of this torus. And we decomposed GC as TC ZXM. Alpha and phi GC or GC alpha is P is a subset of PC star during PC, and we had a subspace which is not defined, and phi alpha and phi alpha of H, and we introduce an order on the real dual of this space H, and so that we could talk about positive and negative groups and also simple groups. So I will note that phi plus minus positive respectively negative groups. This is the set of groups. It's a subset of H star. I'm writing for a subset of H star. H. Phi plus and minus are the positive groups, and we had a subset delta phi plus, which I call simple groups. And we also saw alpha is in delta. If alpha cannot be written, if alpha is in phi plus, and alpha is not equal to beta gamma with beta gamma phi plus. Beta both in physics. That was what the definition of groups. We also saw that every element of P plus can be written as a sum say this. Here's the sum. F3 alpha, and delta. It's alpha integers. This denotes non-negative integers. I think that deviates from usual notation again holds only for positive integers, natural numbers. Deviates a little bit from usual notation. I want it to 0 as a natural number. After all, I'm Indian. We invented 0. So okay. And phi alpha in the all the so similarly of course if phi is in phi minus, we're going to get the same thing. This phi alpha now become all integers of course and the same. Okay. This is the background notation I need, some of which just now told you what they are, but maybe I've not said everything that needs to be said. You have to go back to my last lecture. Okay, so now at this point I want to introduce the while group of the compact group G, which is 50. To do this, one can do it entirely in the setup for the Lie algebra, but ultimately my aim is the wide character formula. It's in terms of compact groups. So we'll have to keep talking about compact groups, even though the structure theories can be done without any reference to a compact group. But I will keep in mind that my Lie algebra is always the complex equation of the Lie algebra for compact group. That's what my aim is to do something about compact groups. Okay. I want to talk about the while group of G of T. But this, I do the part. This is defined as the group NT by T, where N is a normalizer. Is NT is going to be NT is going to be set of elements G such that GT G inverse equals to that along with the T. Now, in any Lie group, a closed subgroup is itself a Lie group. It's a bifold with the induced topology, and because of that, that's what's happens there. NT is a closed subgroup G. It obviously contains T. T is aperiod, so inner conjugation will be T is equal to T on T. So it contains T, NT contains T. And turns out that NT by T is finite. Called the while group. Denoted there. Finite group called the while group. Okay, now it turns out that why is this finite? Is it because look at the NT goes into the inner conjugation, takes it into automorphisms of the torus. Now, the torus is simply a product of circles. and lot of the torus, start lot of the torus, you can get mapping the torus, fix one factor, one circle factor of this torus, apply the automorphism, then project to another factor of the torus. But it's a mapping of the circle to circle, which means it's an integer. Any mapping of homomorphism of circle to circle is raised into some power. It's an integer. Gives you an integer. So if you take there is the torus, there is the circles 1, 2, 3, S1, S2, S3, Sn, and then you get the matrix of integers Tik by looking at one component and project to another component, the ith component to jth component after applying the automorphism. So every automorphism gives rise to an integral matrix. Okay? So this gives a mapping. This in terms of is nothing but GL RC R rank group. That dimension of T. So it's a product of R circles. So if you get an automorphism, it results in a matrix. The fact it's an automorphism, it's an endomorphism, you get a matrix. If it's an automorphism, you get an invertible matrix. So we get a mapping of and GLRG is natural topology, in the discrete topology, integral matrices. You can't do anything better than that. So you get a mapping of this.
This is not clear to me. You are meaning NP, and this is inner topology.
Sorry?
This is not clear to me what you have explained. Can you explain this once more?
All that I am saying is this, okay.
Yeah, this is
And then you have the automorphism.
yes.
Any such automorphism is a
Okay.
n squared of mappings of circle to circle, which gives you integer. And the fact it's an automorphism, it gives you a matrix of says it goes into GLRs. And it's easy to see that this mapping is continuous from the topology on NT into the discrete topology on GLR. Now NT is a compact group, and this is a discrete group, so the image is necessarily finite. And the kernel of the map is precisely those automorphisms which are trivial on T, which means it's precisely T, because T is maximal abelian. You're looking at a little G in the group which normalize the torus, and those which are the ones which act trivially on the torus, then those which commute to the elements of the torus. And we have seen that the maximal torus is maximal abelian, so they must belong to the torus. So this gives you a mapping, injective mapping. That. Sorry? This is surjective, yes. This is injective. Because I have factored through the kernel. The mapping of NT by T into GLRG is injective. NT by T is a compact group, and it's an injective map to GLRG. It follows it has to be finite, because any subgroup, compact subgroup GLRG is necessarily finite. Image compact and discrete implies it's finite. So W is a finite group. This finite group is called the Y group. Before I go, we just want to tell you what happens. The case with G. Sorry? Can it be what? Subjective. G and Z is infinite. There are lots of invertible integral matrices, except n equal to 1. Okay. The case, sorry, GLRZ is, in the case R equal to 1, it's plus minus 1. Otherwise, it's both. Okay. So, in particular, if the rank G is 1, this group is W, is a subgroup of If you prove it's non-trivial, then of course it becomes precisely Z by 2 in that case. And I want to concentrate on this case, but before that, take G to be equal to S1. One knows it's a simple compact group. Always, of course. The group, you can think of this as a matrix group consisting of what? Where matrices, this is equal to P, G, and C. T star T. T star is the complex conjugate of P, complex conjugate transpose P. And this is equal to 1, and determinant P. This is the group. This is the group S1. I'm realizing it is a complex subgroup, but it's realizing the subgroup of a complex subgroup, but it's only a real subgroup of a really subgroup of a complexity group. Oh, this notation is bad. In this case, what's the maximum force? The diagonals we assume constitute the maximum force. What is the group which normalizes the maximum force? If a group normalizes this diagonal matrices, the vector space decomposed into eigenspaces for the diagonal matrices. And anything which normalizes this torus must permute these eigenspaces. In other words, if sigma is an NT and P1, E2, Pn is a standard basis, of NT of the vector space Cn, then you will have sigma, the eigenspace CEI will go into some sigma Ej. Continuous eigenspace so let's do like this for some j. Which really means, if you like, I can write this as for some permutation sigma of 1n to 1n. So each element of the while group defines a permutation. And it is easy to see that the permutation determines the while group. In order to make sure that what you get is unitary, you have blocks of determinant 1, you have to put in a sign plus minus. What you can do is to put the sigma can be referred to this map. The sigma can be this map. It's E2. You have to correct it by the factor like it's the signature of the permutation, which ensures that you get determinant 1. The determinant of permutation itself is not necessarily 1, it's either plus or minus 1, but if you plug in the signature, then it works out right. Okay, so this shows, in the case of the group G equal to G1, the while group is nothing but permutation. I am used to writing the permutation group with that letter, it is the German S, or what it is. Sorry? Elements, what does alpha can it be? Yeah. I'm writing sigma EA is sigma I. Anyway, what was? Yeah. So the case of the group S1, the permutation group is nothing but while. And we all know that the permutation group is generated by transpositions. And in fact, it's enough to look at the transpositions I plus 1. They generate there is a generalization of this statement that the continuation group is generated by this transposition J, which is really, if you look at the vector space, it's a reflection in the plane, which is perpendicular to line join ET. It's a group. So, in other words, the while group here is a group generated with reflections. And an entirely similar statement is true for any semi-simple E group, which is what I'm going to describe. I will not go into the detailed proof, that is more complicated, but I'll tell you what the statement is. Now, point is this: suppose alpha is a group. Alpha determines the rank one subgroup of GC. What is the rank one subgroup? Namely, you look at G, C alpha plus, let's represent what this is, C H alpha plus GC minus alpha. We've seen that these two are one dimensional, and this is one dimensional by definition because I picked up a vector H alpha. What is this vector H alpha? H alpha is a unique vector in H such that H alpha equals alpha H. This is the killing form on the Lie algebra, restricted to Lie algebra H, and the rest we know is positive definite. On I times H, which is T, it is negative definite, so it has to be positive definite on this. It's positive definite, and therefore there is, for every alpha, there is the H alpha such that this happens. So I pick up that H alpha and look at this space. And it's easily checked. It's a Lie subalgebra. It's three-dimensional Lie subalgebra. With a, you can pick a basis E alpha in G alpha and E minus alpha in G minus alpha, such that E alpha, E minus alpha is 1. If you pick up as a basis, you get a three-dimensional subalgebra. And this three-dimensional subalgebra we've seen is isomorphic to SL2. So modify this basis by scalars, you get a basis, get basis E alpha, H alpha, E minus alpha, such that bracket H alpha E plus minus alpha is plus minus 2 E plus minus alpha, and E alpha E minus alpha equals H. That is it. You can modify E alpha, the capital E alpha, E minus alpha, and capital H alpha. By a scalar, you can get down to a basis like what we did, the standard basis for SL. E F H is what I call it. So here I am calling it E alpha, E minus alpha, not F alpha, but sometimes I may call it F alpha. I may also write E minus alpha. New notation. Okay. So we have found this. These are all the E alpha, H alpha, E minus alpha are all real scalar multiples of E alpha, E minus alpha, H alpha. So they span a real Lie algebra, which is same thing as SL2R, instead of SL2C. And then if you replace this by change this basis to IE alpha, IH alpha, IE minus alpha, you get a basis of a compact Lie algebra for compact group dimension 3. That is a real Lie algebra spanned by I times alpha I times H alpha I times F alpha is isomorphic to S U2 linear algebra S U2. Now, and that's obviously true. This linear algebra S2 comes with an inclusion which depends on alpha, is alpha I alpha into G, taking diagonals into a one-dimensional torus T alpha contained in this is a check. I mean, the way we arrived at the linear algebra of SL2C was to take the linear algebra of the original compact group. Sorry, the way we arrived at the G alphas, etc., was to start with the torus in the compact group, to the linear algebra, and then take its complexification. And we are essentially reversing the process. After locating the three-dimensional subalgebra over complex numbers, we have now got the three-dimensional subalgebra over real numbers, and that's the corresponding results inside. You have to show you what you have is the following. You have this real algebra. So this I alpha we treat. How do you get a homomorphism? The point is you have a homomorphism of this real algebra, which is the real algebra of SU2, into the real algebra of the group G. We started with something which goes into GC, but we have modified it by that I, and so it goes into the corresponding compact layers, real algebra of the compact. So this, what I want to say is this inclusion here, inclusion. What I call it? Yeah. I alpha. What that will become SL2C into GC gives an inclusion which I continue to note I alpha from this subalgebra SU2 to G. The original compact group. Hence, by fundamental theorem of this theory, you get a homomorphism which I call I alpha, and the corresponding G group is it's a simply conductor group. SU2 is simply conductor. SU2 is nothing but a sphere. You can think of SU2 like a unit coordinates. So this is a simply conductor group. Any real homomorphism gives the mark of the SU2 the corresponding group G. That's what I call I alpha. And I alpha, it is also easy to see that I alpha takes the diagonals, which is the maximal torus in SU2, into the torus T. That's because the way we are concerned with both. It's easy to see. So what happens is this: for every group, we have a corresponding map of the group SU2 into the group G, taking the torus of SU2 into the maximal torus we have already fixed. Yeah, I don't care. I'm just saying. I just say it's injective. I have small, lowercase I alpha is injective, not higher case I alpha need not be injective. No. You get the homomorphism. Now, in SU2 we have a special element which I call small w. This element has the effect of permuting E1 and E2 between them. E1 goes to E2, E2 goes to minus E1. You know, when I identify things with the permutation group, I have to put in a signature to ensure it is a determinate one. So that's why 0, 1, minus 1, 0. The permutation matrix itself will be 0, 1, 1, 0. But put this minus 1, 0, that ensures it's in SU2. And it clearly normalizes the torus. And the image alpha W is what I call W. It's the white element. It's corresponding to the root alpha. Notice that if you put in minus alpha, it may be the element that you get is what you get from I alpha, but with minus 1 plus 1. This slight interchange that takes place. Minus 1 plus 1 is this element W, W squared becomes minus 1, minus identity. So only the fourth power is 1. So it's inverse. I minus alpha becomes W alpha. I minus alpha is not W alpha but W alpha is inverse. It's a minor matter. So, but how does W act? Now, also note that W is actually going to be and see what we have done is this essentially this how do we get this sorry I want to say W alpha is the name. What it does is the following. The image of I alpha of diagonals is a torus, is a dimension 1 torus. It's a right superscript alpha. Subscript alpha was defined as the kernel. And then if you look at kernel of alpha as a mapping from G to the circle group, kernel alpha and T alpha will intersect trivially because the T alpha, the T superscript alpha comes as an image diagonal here, and the diagonal element here is something supplementary to the kernel of alpha. This may look a little complicated, it's not, it's a very indirect thing. Kernel alpha is this, and T itself, kernel alpha, kernel alpha will be correct identity component of kernel alpha. Is what I call T alpha. The identity component of the kernel of alpha. Kernel of alpha need not be connectors, but it's a subgroup of the torus. Its identity connected component will be a torus. A torus of codimension 1, because alpha is a linear form, and the linear algebra takes the kernel of that homomorphism and take the corresponding V2, and so T becomes equal to T alpha times and the well programmed W alpha. What it does is to fix T alpha and act as T is going to T inverse on this W alpha T times S. This is in T alpha, and the other one is T capital alpha. This is inject, this is going to be T times S. Notice that T subscript alpha.
Please just explain again what is the lower and upper alpha.
The lower alpha is the kernel from T plus 1, and the upper T alpha is something which comes from the SU. At the real algebra level, I am looking at the kernel of alpha, and then that's I'm thinking in terms of the real algebra like H. So you look at the kernel alpha on H, and then you look at the element H alpha, it gives you one-dimensional space. And alpha is not zero on H alpha, so the whole thing is a direct sum of H alpha and the
So you got the n minus 1 dimensional kernel, which is the lower one, and the
right, then one dimensional. And when I go to the group, when I go to the torus, the intersection can be non-trivial, can be finite. So I can only write this, it's not a direct product. However, decompose it like this. And what W alpha does is to W alpha actually centralizes everything in this. Yeah. First, the group, the G alpha we constructed is in centralized of this. So W alpha is in centralized, so it fixes that. And on the complement we see that it acts as that E1 going to minus E2, E2 going to E1, something. Okay, so that is the. So you have now identified certain special limits W alpha in the while loop. W alpha normalizes T, so W alpha goes into while loop. For every alpha, you got a special limit W alpha. Every alpha get the limit W alpha of NT, which is such that W alpha T. So, if you write it like this, add W alpha of x minus x if x is in the three-dimensional subalgebra. And equal to x if x is in the kernel alpha from PC.
Here, the intersection of P, lower alpha and upper alpha can be non-trivial, right?
Sorry?
The intersection of C
Can be.
But then how does that action makes it? Because I can consider some element, let's just say x is in the intersection.
The common element which may come up is of order 2, so which is equal to 4 inverse. Okay. Okay. That way it works. Now, so add W alpha x acts on the algebra TC and does this. It actually stabilizes the algebra. Stabilizes the somewhere at the bottom. Stabilizes the algebra of the subgroup G isomorphic with U. So the torus itself, compact torus itself, we have this decomposition P alpha times P alpha, and correspondingly you get the real algebra decomposition of P as again I write P alpha. Now it's all real algebras, but it even becomes a direct sum like this.
X going to minus x is not
Sorry?
x going to minus x
Yeah.
is not a linear combination of x and 2.
No. That is being done only on the total part. I am describing it only on the torus, the of the torus, which is abelian.
X belongs to intersection of torus with that freedom.
If x is in kernel DC, see this is go. This is the three terms thing. So if x, sorry, I wrote it wrong.
You don't want the G alpha.
W alpha x equals x. If x is in what I call P. So the torus itself breaks into two parts. One dimensional, the other. On the one dimensional part, it acts as -1. On the other part, it makes a reflection. This reflection of the hyperplane, where on which the group actually W actually. So you've got a number of reflections. Correspond to each group, you get a reflection.
Basically, the kernel over here, but we can make a hyperplane along which we are doing the reflection.
Sorry?
The kernel, like I get it, the
Yeah.
lower would be like the hyperplane along which we are doing the reflection.
It's a hyperplane, yes. I'm reflecting the hyperplane. I mean, so the reflection is usually always refers to hyperplane. If the reflection is identity on a hyperplane and 0 in orthogonal direction. The orthogonal. It's not sorry, it's -1 in the orthogonal direction. The unusual idea of a mirror reflection. Okay. And now start a string of theorems for which I give no proofs but get statements. W alpha n delta generates the Y group is generated with reflections, like we saw as it happens in the perturbation group. And if you take the transposition where muscular elements are involved, that corresponds to reflections in simple group, reflections coming from simple groups. But SRN, for SUN, you can talk of again. You take the diagonal matrices that gives you it gives you the maximal torus, and it's really derives simply the diagonal elements of trace 0. And you look for, and on that, how do you get reflections? I showed you how the permutation group operates on it. The transpositions particularly operate. Transpositions of successive elements in the basis are the ones which correspond to W alpha, alpha, and delta, simple groups. So W alpha, alpha, and delta generates W. That's the theorem. That's one of the theorems. One proves first, you take all reflections that generate W. Then as the next step, you prove that simple reflections are enough to generate them. This is like the permutation group, you take all transpositions or only transpositions corresponding to successive elements on the basis. Both of them generate. So this is the statement which I want to assume. So this implies a W acts on P, and hence on the group of functions of T, in particular on characters of T. And the kind of functions we are interested in are come from algebraic geometry. I will restrict it to the compact group, of course. W acts on T, and hence on the group is the domain, the group of characters. This is isomorphic. Dimension of you have seen this. How do you get a character on the torus? The torus itself is a product. And all that you each factor you give a character, then you form the product and get a character group, and vice versa. So the character group is nothing but C power L. Because the torus itself is circled to the power L, where L is the rank. So XT is a group of characters, and we call the span, C span, and XT, I call them the regular functions. These are simply linear combinations. So complex coefficients are that. The terminology comes from algebraic geometry. you think of P as part of the algebraic, think of P as a real part of the algebraic variety C star. And then you take polynomial functions of C star or regular functions of C star, restrict them to P, you get these functions. Okay. W acts on this. And I'm particularly interested in two classes of functions. Functions invariant under. Let me call this. What should I call this? Functions invariant under W. FP, which you write as all FP, and functions which transform by the signature of the signature on the I'll proceed to say what it is. These are denoted F A sorry F P W and A stands for alternating. This is the set of functions F and F P with property that S alpha F P S alpha F equals minus or more generally I will not define this F and P, not more generally C for F and P W F equals epsilon W times F. Well, epsilon W is signature. That's a function which is similar to the signature of the commutation case. How do you define it? You simply define epsilon W is determinant of W acting on the real program, which I call the while group operates on the torus T, and therefore on the real as auto therefore on the real, right? So you get maximum. And if you look at S alpha, it's a on T the axis by reflection. And the reflection is determinant 1, which I call epsilon of S alpha. That extends the entire while group. It's easy to do. And that is what I call signature in analogy with what we do with permutation groups. It's figured elsewhere. So this is the set of functions which are like alternating with respect to W. These are functions which are symmetric with respect to. Okay. Now, if you take a if rho is a finite dimensional representation, at G, we set chi rho to be the function of the group. Chi rho of G equals trace rho G. It's called the character of rho. It's a function of the group. Trace rho G for G. This is the I already told you that the character of the representation determines the representation for completely reducible representations. So chi rho G, if we know chi rho G, we know the representation immediately. Now, chi rho G itself is determined by restriction of by node to T. Because we know that every node has a conjugate in T. So if you want to know what value of G is, just take the conjugate in T, and that is the character. Because this value is stable, is invariant in the inner conjugation. Moreover, value should be symmetric. Because when you conjugate by an element of the Y group, what happens? It keeps T stable, so it maps functions on T into themselves. And you apply the Y group element to the whole group, and then restrict. That's the same thing as applying the Y group element on T itself, and you get the same result. So you first start the function F and restrict it to T, apply the Y group. That's the same thing as apply the Y group early on, restrict, and then you get a function of T. So it's compatible. So what you get is a symmetric function. The function is invariant integrative. Conversely, if you have a function which is invariant in W, it extends to the entire group. This is a little tricky because the function may be regular on T. The extension is immediately defined because the elements are conjugated in the torus. So you can define the function to be corresponding function of the corresponding element to the torus. But if two elements are conjugated in G, but they belong to T, you have to know that they are already conjugated in T to be able to make the extension. That is true. Little tricky to prove, but not very difficult. And even if you extend the function, it's not clear the function is booked on the whole of G. The function may be booked on the torus, but the extension, first say the function is continuous on the torus, the extension is continuous. It's not clear. It's true in this case. So basically, the characters are determined with various symmetric functions on the torus. What Weight's character formula does is to tell you, given a representation rho, it tells you what the corresponding character on the torus is. So therefore we wrote down the position. So determining the character of a function, the character of a representation is the same thing as is knowing it on the torus. And the formula M1y tells you to a given representation what the character restricted to the torus is. That's a theorem.
So,
It's a symmetric function. Sorry?
so what is the extent of the Y group on those regular functions?
No. It's a name. The C span is what I call a function in the C span is what I call a regular function of T. That's just a definition.
You are asking the action
It's
of
a
the
definition. So,
You are asking the action of the Y group on functions.
Y group on regular functions. Y group acts on xt. It acts on characters and therefore linear span of characters. I must say that characters on the torus are all linearly independent. Distinct characters, you take them on, they are all linearly independent, you won't see. So what you get is a free vector, it's a vector space with xt as basis. It's in fact, if you think of xt as Abelian group, what you get is the group algebra of xt. This is ft is nothing but group algebra of xt. So where was I? Yeah. So that I told you what the Y character formula tells you is this. Now, of course, this is no big deal. How do you classify representations? Somehow, if you have a table representations, then to this representation you can say this character corresponds. Okay. So what one is going to do is to first describe. This is the last lecture. I don't know. I will have to ask for one more lecture. Anyway,
You
so
have just 5 minutes left.
I will stop.
Yeah.
Hey, I'm going to stop. This is last point. So that's why I'm saying I need another lecture to complete this business. After that, you will have to find my time for me. Is there still what do you call it? Tutorial?
Yeah.
I'll take that over for a lecture. Actually, you're right to laugh because I've been doing it anyway. So let me just make this statement. What we're going to do is to show that a certain family of characters on the doors, a certain subset of this set of characters on the doors, can be used to parameterize all representations of G. There are what are called dominant characters on the doors. The dominant characters on the doors are bijective correspondence with irreducible representations. Since I have grabbed one more lecture, during that lecture I will describe that whole thing, how you associate to each dominant character a certain representation of the group, and then from the dominant character is a character on the doors. So from that dominant character, how to get the character which gives the character and the representation of the group. So we have row, and to this you have associated by row. What happens is this: you have seen dominant character, you can associate this representation rho lambda, and to this rho lambda you get. So the why character formula tells you how to get hold of dialogue in terms of lambda. These are what are called dominant characters. Right? And give a description about this, and probably also can only end up stating the bias character formula, not proving it. That's where it has to end. Thank you.